Hello and welcome everyone. Today this is the question that we are going to deal. I have simply opened the application question page, and this is something that we will be requiring later on during the solution to our program. So let's click OK. For that, file, new, and let's choose the units kilonewton, meter and Celsius. Choosing the right unit is important. And have a look at our question. It has a total span of 12 meters. And the supports are not at uniform distance. That is, it is at 8 meters from the left end and it is 4 meters from the right end. So choosing the beam may not be the right option. So let's go for creating the beam from scratch. That is, let's go for grid. Since it has 12 meters of span, we need 13 grid lines. In X direction, in Y direction, let's put 2 grid lines just for the sake of sense of the direction, and 2 in Z direction for the same. And grid spacing, let's put grid spacing to 1, that is 1 meter, 1 each, and click OK. Now this is the grid that we are left with, that we created. This is X direction, vertical upward is Y direction, Z direction, and inside is Y direction. So we don't need the 3D viewer at the moment, so click on, just click it closed. Now, and we are left with the XY plane. It is important to know which direction the axis mean. This is horizontal. This horizontal plane will be XY plane, and this vertical will be the direction of Z axis. So we are going to deal with XZ plane. Now let's go for creating the beam. Click on this tool, draw frame cable element. We don't need this at the moment. Click on the starting point, click on the end point, and simply right click. Click here. Now let's assign restraints, or let's put a support to this point. Click on this point, assign joint and restraints. It is a hinge support. Yeah, so this is the symbol for hinge support. Click on hinge. It's already selected, so it's fine. Click OK. Now we get the symbol of hinge support. Now at 4 meters from the right, we have another support, which is a roller support. So let's create a joint in there. Get it closed at 4 meters from the right. That is 1, 2, 3, and 4 meters. Click here. Select joint and assign restraints. Joint and restraints. And this is the symbol for roller support, and the restraints for the roller support are automatically selected. Click OK, and you can see the symbol for roller support. Now we are done with creating the beam. Now let's go for assigning the loads. Let's start from 50 kilonewton. Select the beam by clicking on it, assign frame loads, point. Now you can see 2 radio buttons. One is relative distance from in I, that is in left, and absolute distance from in left. In relative terms, you can see here 0.25, 0.75. They are the distances from the left in proportion. The rightmost end is 1 and leftmost end is 0. Rather than that, absolute distance is relatively easier to use, so let's go for absolute distance. So at absolute distance 12 from the left end, let's assign 50 kilonewton load. 50 kilonewton, it's here, and the direction is gravity, vertical downward, that is and it's force, so we don't need to change anything. Click OK. Click here and you can see the 50 kilonewton load acting vertically downward. Now let's go for assigning the 6 kilonewton meter UDL. Assign frame loads distributed. Make sure you select, then its force again, and in the direction of gravity again. Click absolute. From 0 to 4 it's 0, and at 4 it raised to 6. At 8 it's 6 again, and at 8 it drops to 0. From 0 to 4 up to 4 it's 0 to the left, and from just right of 4 it's 6, to the left of 8 it is 6, and from the right it's 0 again. So add the existing loads and click OK. Now this is the load, that way just assigned. Now let's go for assigning the moments. Select the beam, assign frame loads. Once its point load acting specifically at these and these points, so its moment and the direction. The direction of the moment is very important. It is in this way, anti-clockwise direction. This couple and the direction of movement is given by the right hand thumb rule. It's the direction of couple. It is trying to rotate in anti-clockwise direction, and if you press this portion of your right hand here, then this thumb will point perpendicular out of the screen towards you, that is in this direction. You must have noted that the direction of the y-axis is this, in this direction, but the direction of movement is this, so it's in negative y direction. So choose y at distance 2 from the left end, it's minus 20, and at this distance, and this is at distance 10 from the left end, and this is clockwise, just the opposite nature of this couple, so is 20. Add to existing loads. Everything is done. Newton meter unit is well selected. Okay. You might be wondering why is that not being displayed. To see that, you can simply click on the 3D view, and these are the moments that we just assigned. Back to XZ view. Now the tricky part of the question is this incline load. To place this, let's first allocate the location for it to be placed. Click here, make it a joint. Since we don't want this point to act as any of support and just act as a point of the frame, let's click assign, joint and restraints. We don't want it to resist anything, so click on point. Now it simply is a point on the beam. Now select the point or the joint and assign joint loads forces. Make sure you select local axis. We'll talk about the local axis in a while. The local axis has 3 axes, x, y, and similar to x, y, and z. There are 1, 2, and 3. 1 for x, 2 for y, 3 for z. Since the load, this 40 kilonewton, is acting downward, let's write minus 40. Z direction is put upward, so in downward direction it's negative of 40. And click OK. Now it is acting vertically downward, but we need it at an angle of 30 degree with the horizontal So select the joint, assign joint and local axis. Now we have to rotate the XZ plane by an angle 60 degree. To get a 30 degree with the horizontal, we need to rotate the XZ plane by 60 degree. Since we have rotated the X and Z plane, choose the axis of rotation which does not have both of them, that is Y. So it's 60 degree clockwise direction and it's positive. Click OK. Now the axis being shown in red and blue are the local axis. This is the local axis for this point, this is for this point, and this is for this point. The other three local axes are not rotated and are parallel to the XYZ axis, but this is rotated by 60 degree. Now let's see how the force is being applied. Joint and click OK. Now it's being applied at 30 degree with the horizontal. I think we are done with the assignment jobs. Now let's make sure that the weight of the beam is not being calculated. We don't want the weight of the beam to act as load, so let's neglect the weight. To do so, assign frame sections, and this is the section of the frame that is being applied. So let's modify its properties, set modifiers, and let's set each of mass and weight to 0. Click OK. If you need to change any other properties in some other questions, then you can select section properties from here. Now click on OK. OK, and this is the name of the section being applied to this frame, to this beam. So we have done almost everything. Now let's analyze. This model analysis is for earthquake analysis, and we don't need it at the moment. It is beyond our scope right now, so let's not run this and click on run now. It will prompt you to save the work before running analysis. Now let's give it a name. MOTRA 57. It's already there, so let's keep 57A or any name you like and click save. It is the deformed shape. Now we are concerned with the bending moment, axial force and shear force diagrams. So click on this drop down arrow, frame cables, and okay, let's go for axial force first. Show values on diagram. It will show the values and click OK. Now this is the axial force diagram for the beam. It's minus 34.64 up to this point, and no axial force acts in this direction. For shear force, shear to 2. Okay, and this is the shear force diagram. 4 and it's 24 up to here, and increases to 48 minus 50. This is the shear force diagram, and for bending moment diagram, this one. This is the bending moment diagram, and this does not look quite good at this scale, so you can change the scale to the one you like. Let's change it to twice or thrice, let's say. Okay, now it gives a better view, and you can always zoom by scrolling your mouse and get the values. Now this is the analysis that we got from the application SAP2000. So let's compare the values with the solution, and this is the solution done in Matra source book. Now this is the bending moment diagram. So it is 8, it is minus 8, it is shown here, negative minus, and shown in red, that means negative. This is minus 8, this is minus 220, and at this point it is 99 point something, means it's 100. Or if you want specific values at different points, you can simply right click the beam and it shows all of those. This is the deflection curve that will be studying later on. So this is the, and if you need specific values, say at this point to the left and to the right, we have different values. So this is at 2 meter from the right end, means 10 meter from the left end. Let's do 9.9999 meter, and it shows at this point it's 120. It's 120, and just to the right it has dropped to 100. So it's 10.00001, and it's 99.9995, means it's 100. So in this way you can see the bending moment diagram and other as well. Let's compare the other two diagrams as well. Shear force diagram, and it's 4, it's 24, means it's 24 up to here, and increases to 48, and is 50. And axial force diagram, axial force is minus 34.64, So this is what we needed, and that's it, we're done. Go ahead, try it yourself. All the best.